Okay, welcome back. This is now 3.2, and we're continuing on with predicates and quantified statements. We're going to want to negate them. Okay, so 3.2, predicates again. And this is basically part 2, predicates and quantified statements, part 2. So first off, looking at the negations of these things. And to note the relationship between a universal and a quantified statement, the book is going to, well, they talk about it a little bit. So let me just note that very quickly. Suppose you have a domain of elements, let's say x1, x2, etc., all the way up to x sub n. Okay? And then our universal statement says for all x in this domain D, q of x. Okay, so what does that mean? It's really an and, a long conjunction. It basically means that q of x1 is true, and q of x2 is true, and on, and q of xn is true. Okay. Okay, so how can I connect this maybe to the existential? Well, via a negation, you know, De Morgan's would turn this into an or statement, right? So if we apply De Morgan's law and negate the thing, we would end up with the statement not q of x1 or not q of x2 or dot 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 or not q of xn. Okay, so for this to be true, there would have to exist at least one not q of x1 that was true. In other words, there exists an x in the domain D such that not q of x1 is true. Okay, and that's kind of the relationship. To go from a universal statement to an existential, you negate. Okay, and so when you do this process, wherever you see a universal, you're going to change it to an existential, and vice versa as well. And I believe it's because of this relationship between the ands and the ors and De Morgan's law. Okay, so hopefully that gives you some intuition on why. Let's look at the actual negations now. Okay, so I don't know, symbolically, we have the negation of a universal statement for all x in D, q of x. Okay? That's going to be equivalent to saying there exists an x in D such that not q of x. Okay? So what, you know, mechanically, what's happening is you're just, for the sort of initial statement here on the domain, you're flipping the universal into an existential, and that's it. It doesn't change the domain. It doesn't say all of a sudden x not in D or anything crazy like that. The only thing that's affected is the existential. The universal turns into an existential. Okay, and then you're going to negate the predicate part. Okay, so you change the comma into the such that symbol. Okay. Okay. On the other hand, when you negate an existential, well, it's pretty much the same deal, right? And of course, we need a bar there instead of a comma. You'll change the existential into a universal for all x and D. Don't mess around with the domain part. That's not affected. And then negate the predicate, whatever that is. Okay, and that's it. So let's try to get in there and do maybe one or two of these problems. Let me find where they are. Okay, so we'll look at number 3. And the book wants us to write a formal negation. Part A says, like, yeah, crud. It changed up the problems on me again. Sorry, one sec. Okay, so yeah, all right. Number 3, part A, we have for all strings S has at least one character. So this is more of a programming example. So a string is just a bunch of letters or numbers, like a password, something like that. And they're saying that for you to qualify as a string, you have to have at least one character. Like if to qualify as a password, you have to have at least a letter, right? Okay, so I need to negate this statement. So I'll say there exists a string S such that S has no characters. And one thing about these negations, if this is true and you negate it, this statement will be false. Okay. Let's look at another one. I don't know. Let's start part B. No, let's do part C, because that will be an existential. Okay, okay, so part C, there exists a movie M such that M is over 6 hours long. Okay, so the negation of M being over 6 hours long would be M being less than or equal to 6 hours long. Okay. All right, so the negation for all movies M is less than or equal to 6 hours long. Okay. Let's look at some other ones. So number 4. This time they want kind of an informal version of the negation. Be careful to avoid negations that are ambiguous. Okay, so number 4, part A. Says all dogs are friendly. So the negation will be an existential. So there will exist a dog that is not friendly. Or maybe even more informally, there is a dog that is mean. Okay, something like that. Let's look at another one, part B. All graphs are connected. So we should be doing some graph theory later in this semester. Graph theory is a lot of fun, but unfortunately it's kind of hard to take graphs and put it into a more symbolic kind of English type symbolic notation. So that causes a lot of headaches. So it's not as, oh my gosh, we get to do graph theory. Yeah, kind of, but at the same time, it's going to be difficult just because of its intrinsic properties. Okay, so anyways, all graphs are connected. There exists a graph which is not connected. So there is a graph which is not connected. Okay, so kind of simple. I don't know. Let's see what else we got. Negations of universal conditionals. Right. So a universal conditional, remember, for all x, if p of x is true, then q of x. Okay. So to negate this thing, we're going to have to remember, and I was talking about this in the last section, I should have talked about in this section. You have to remember how to negate if-then statements. So recall, either you get the work, if you get the work on time, if you don't get the work on time, then you're fired, right? That's equivalent to saying either you get to work on time or you're fired. If you don't get the work on time, then you're fired. Either you get to work on time or you're fired. Those are equivalent statements. So I need to negate them. Okay, so negate this thing. And basically it's De Morgan's. So this will turn into P and not Q. Okay, so to negate this thing, we just flip this universal to existential and then turn this into a conjunction like that. Okay, so this will be there exists an x such that p of x is true and not q of x. Okay, so let's look at some of those maybe. I think it's number 9 I want to look at. Let me make sure. Yeah, so write the negation for the statement, and the statement number 9 is given as for all real numbers x, if x is greater than 3, then x squared is greater than 9. Okay, so there exists a real number x. So remember, all you have to do is change the universal into an existential. Don't mess with the domain. Such that, and now we change the if-then into a conjunction, right? So x is greater than 3, and x squared is, to negate this statement, you just take its complement less than or equal to 9. Okay. Let's look at number 18, I believe. Yeah. This time it says for all x in the real numbers, if x times x plus 1 is greater than 0, then x is greater than 0, or x is less than negative 1. Sorry. So I don't like to use any words at all. It's a preference. You can do it that way. So long as somebody can read your work, it's fine. Generally, though, what I would have to do when I was like taking abstract algebra is I would translate everything in the symbols, do my proofs, but then at the end have to translate back everything in the words so the grader could read it. Yeah, bit annoying, but okay. So anyways, I want to negate this thing. So again, just turn this into an existential. There exists an x in the real numbers such that, and now I want to change this into conjunction. So you keep this the same. So it's x times x plus 1 greater than 0. And here it's a De Morgan's law, right? So this is an or. To negate this part of it, I'm going to have to change this to an and I'll have to negate both of these sides. Okay, so instead of x greater than 0, it's x less than or equal to 0. And instead of x less than negative 1, it'll be x greater than or equal to negative 1. Okay. Uh, 22. if the square of an integer is odd, then the integer is odd. Okay, so first I'm going to translate it into symbols, and then I'm going to negate it. That's a little easier for me to do than just working, again, with the English. It's, symbols are sometimes a lot better. So for all integers x, I'll say, for all, let's make it really symbolic, right? So for all n in z, if the square of the integer is odd, so how are we going to write that? If n squared is, I guess we could just say, let's make like a predicate operation, right? So we'll say odd of n squared. That means if n squared is odd, then this will be true. Okay? So if n squared is odd, then the integer is odd. Okay. Okay, so you just make up some functions where the input is the number we're talking about. I want to negate it, so I'll turn this into an existential. There exists a number n in the integers such that, so now I change the conditional into a conjunction. So I'll say n squared is odd, and it is not the case that n is odd. Okay. I don't know. Let's look at another one. Oh yeah, converses and inverses. They'll kind of embed those here as well. So let's see, 32. They want you to find the converse and inverse for problem 22. Okay, so 32. First find the converse. And it doesn't affect the universal or the existential part. What it affects is this implication part. So the converse, remember, is just kind of reversing the order of the implication. So the converse would be for all n in the integers. If n is odd, then n squared is odd. Okay. Then likewise, for the inverse, that's where you just negate both of these in the implication. So that'll be for all n and z. If n is not odd, then n squared is not odd. So we could write it like that. One thing I hadn't talked about, vacuous truth. This becomes a nightmare if you ever take like real analysis. You're looking at, what is an empty set open or is it closed? Those kind of questions. If there's a set that has nothing in it, is it open or is it closed? Like on the real numbers, we're kind of familiar with open sets. Those are the ones that look like this with open parentheses. So this is an open set. This is a closed set, right? But then what about sets that don't have anything in them, like empty sets? Is that open or closed? And we can make statements like saying that it's kind of vacuously true that it's open because it doesn't contradict the logic. And so we want to investigate that before you get thrown into the deep end. So a good example here, problem 38. Is this true or false? All occurrences of the letter U in the words discrete mathematics are lowercase. Okay? So what did they just say? All letters U in discrete math, and the phrase discrete mathematics, I'll just abbreviate discrete math, are lowercase. So the deal is there are no letter U's in that phrase discrete math. Okay, so they'll say it's vacuously true. And generally the way you can kind of trick yourself into believing that is to look at the negation of whatever thing this is. So for example, if I rewrote this in terms of a universal, what would that look like? For all letters U, U is, if U is in discrete math, the phrase discrete math, then U is lowercase. Okay, it's vacuously true because U is not in here. Okay, so it's kind of like a false, and the only way it would be true is if this was true and then this was false. I mean, see, the only way it would be false was if this was true and this was false, but it's more of a false situation. Okay, but if you don't think, you can also think of it by negating it, and then it becomes painfully obvious that it's not because its negation is the negation is not true. The original statement must be true. Okay, so look at the negation. There exists a letter U such that U is in discrete math. And U is not lowercase. Okay, so clearly in this case, it's going to not work, right? There are no U's in discrete math. Okay, this is saying there exists one. No, there's not. So this is just patently false. So the way these universal existential statements and the negations work, if the negation is false, then the original would be true. So if this is true, then this has to be false. If this is false, if the universal is false, then this has to be true. Okay, it's just going to work that way. So this is definitely false. That implies that this has to be true. Okay. So if you're trying to figure out one of these weird cases, like is the set open or closed, you can think in terms of universals and existentials and do negations and kind of find a setting where it becomes obvious that it's either true or false, and then make your conclusion there. Okay. The book is also going to throw in the necessary, sufficient, and only ifs in here. It's a little weird because they won't kind of introduce the statement as a universal. But just remember the sufficient condition, R is a sufficient condition for S, is basically saying if R then S. Necessary condition, R is a necessary condition for S, is basically S, if S then R, and then only if is if P then Q. P only if Q is the same as P, if P, then P only if Q is the same as if P then Q. Okay, you may have to go back and look those up again. Again, I'm not a big fan of these kind of questions, but they are in the homework, and I just want to remind you very quickly. So remember this, so if you're given P then Q, the necessary P is a necessary condition for Q means Q then P. This is just straightforward P then Q, and then this is straightforward P then Q. Okay. All right, so 45, they want you to rewrite the phrase without the sufficient condition part. And so let's look at it. So having a large income is not a sufficient condition for a person to be happy. Okay, so what I'm going to do first is write it as a universal, and then I'm going to negate it to create this phrase here. So for all people P in the set of P, which is the set of all people, I'll assume, if P has money, or P has a large income, then P is happy, right? So it's basically the same statement, but without the negation. So now I'm going to negate it, and it should be a translation of the original expression. So there exists a P in the set of all people such that P has a large income and P is not happy. So it's a little weird working with those. It just seems like in the software when it pops up, they don't have this part of it. It's not explicit that that thing is there, but the problems are in the software and in the homework. But let's look at another one from the book, an example. I don't feel good about this one, but let's look at it. So example, and this will be the last one. We'll leave it at that. Example 3.2.6. Okay, so we want to rewrite the following universal conditional statement quantified either explicitly or implicitly. So that's the weird thing. In the homework, they're implicitly quantified. So you won't see for the phrase for all or the phrase there exists. Okay, so in this example, it's like that. So part A, squareness is a sufficient condition for rectangularity. Okay, so I would say you got to translate that into a for all. Sounds like a for all statement, right? So for all objects X, and then sufficient condition is an if then in the forward direction. So if X is a square, then it's a rectangle. Okay. Yeah, okay. Hopefully that sort of helps. There's other examples in the book, but I know they're in the homework online, so there it is. Okay, we'll leave it at that, and we'll see you next time.